So I want to take a look again at these two very important limits that we evaluated today, two improper integrals that we calculated the integral of today. So we saw the first one was the integral of 1 over x as we go from 1 to infinity. And we saw that this was equal to infinity once we took the limit and solved this integral properly. And the other one was the integral of 1 over x squared as x goes from 1 to infinity. And in this case, we saw that the integral actually converges and the value is equal to 1. So basically what this is saying is that if I was to try and look at the area under the graph of the function 1 over x from 1 to infinity, that area would essentially be infinite. And if I look at the area under the graph 1 over x squared from 1 to infinity, that area would actually just be equal to 1. Now, this can be a little confusing because if I look at the graphs of these functions, right? So let's take a look at the graphs of each of these functions. So if I look at the graph of 1 over x, that graph looks like this. And if I look at from 1 to infinity, so let's go to the number 1. 1 is here. And if I go all the way to infinity, you can see that there's always, as we know, this is a horizontal asymptote. So it never actually touches the x-axis. There's always going to be a little bit of area under here. So it makes sense that if you keep extending this, and if I'm trying to find the area under this all the way up to infinity, that area is going to be infinity. But it also might make sense for us to think about that, well, but if you think about it, the area just keeps getting smaller and smaller and smaller. So is it not possible that all of these tiny areas actually add up to a particular number? So let's look at the graph of 1 over x squared instead. So if I look at the graph of 1 over x squared, now this guy we actually know does converge. So 1 over x squared, the value of the area under the curve from 1 to infinity is in fact 1. So if I start here at 1, and if I go, let's start at 1. Yep. And if I stretch this all the way to infinity, it almost looks like there's no area under here. But if I zoom in, really zoom in, you do see that there is some part that's under this curve. What we're claiming with solving these improper integrals is we're in fact saying that if you were to look at the area under the graph of 1 over x squared from 1 to infinity, this is a finite area. It's equal to just 1. And on the other hand, if we look at just 1 over x, we're saying that this area is infinite. So this is really hard to tell from just the graph, right? If I draw the graph of both the functions, then they look almost exactly alike. So this is why we actually need to do the limit calculation to actually figure out whether these integrals converge or not. It's only when we work out the limits that we find out that for 1 over x, the area actually diverges, and for 1 over x squared, the integral converges. Keep in mind that this is only for the integral from 1 to infinity. I'm not looking at the integral from 0 to 1 or from negative 1 to 1. I'm just looking at the integral from 1 to infinity. What I'm going to do next is I'm going to compare these functions to some other functions. So for some reason, we don't know why, but we worked it out algebraically. We know that the area under 1 over x from 1 to infinity is infinity. And the area under 1 over x squared from 1 to infinity is equal to 1. So let's look at a different power, right? So let me look at 1 over x cubed, say for example. So let me draw the graph of 1 over x cubed. So 1 over x cubed, you can see looks very similar to 1 over x. So 1 over x looked like that, right? And 1 over x cubed looks really similar to that. So if I zoom out, the graphs look really similar. But of course, 1 over x cubed is a little bit steeper. So what I'm going to do actually, I'm going to compare 1 over x cubed. Let's compare all these graphs together. Let me take off 1 over x. So remember what we said. For the blue graph, we said that the area under the blue graph, starting from the point 1 to infinity, was finite, right? It was actually just the number 1. So here's the question that I would ask you here. If the area under the blue graph is a limited number, it's a finite number, then the area under the green graph, what could we say about it? Well, I'd hope that you have come to the conclusion that the area under the green graph is also finite, right? Because if whatever is under the blue graph is a finite number, then whatever is under the green graph must be a finite number. So this is what we do when we compare two functions and we come to a logical conclusion based on something we already know. So because we know that the area under the blue graph is finite, the area under the green graph must be finite, right? So this is the first part of comparison theorem. So I'm going to go back to my notes here. So let's say we have two functions. So I have this on the comparison theorem page in the notes. Let's say f of x and g of x are two continuous functions. And what we know about these two continuous functions is that they are continuous on the interval from a to infinity. So they start at some point a and end, they go all the way to infinity. So in this case, it's going from 1 to infinity. And suppose you know that there is a relationship between these functions such that f is always less than or equal to g. So in the current example that we were looking at, the example is that 1 over x cubed is always less than 1 over x squared when x is in the interval from 1 to infinity, right? So on this interval, we've seen that 1 over x cubed is always less than 1 over x squared. So what can we say? Well, if we're saying that if g of x, the integral converges, then f of x, the integral must also converge. So think very carefully about what this is saying. What it's essentially saying that if I can prove that one of these functions is always less than the other function, so 1 over x cubed in this case is always less than 1 over x squared, then if the bigger function, which is g of x, if the integral of that function converges, then the smaller function, which is the integral of f of x, must also converge. Now, this makes sense because of what I said earlier with the graphs, which is that if the area under the bigger function is finite, then the area under the smaller function must be finite. So that's all we're saying with the first part of comparison theorem. Before we go to the second part, I want to show you another example with two different functions. So let's now look at what happens if you can say one of them is smaller than the other, and if the bigger one converges, then the smaller one has to converge, right? Let's look at what happens if you have divergence. So if I look at the function 1 over x, right? 1 over x we know diverges. The integral of the function from 1 to infinity, we know diverges. So if I compare 1 over x and 1 over x squared, this isn't really very helpful because we know that just because 1 over x diverges, now 1 over x squared is smaller than 1 over x, right? So, and we know it converges. So it doesn't really say anything about the function. So instead of 1 over x squared, let me try and look at a function that is maybe bigger than 1 over x. So let's take a look at the function 1 over x to the power 1/2. So that's the purple graph here. And what you'll see with the purple graph, so let's again go to our favorite point 1. And after the point 1, you see that the purple graph is on top, right? The purple graph is above the black graph. So here's what we know. We know that the area under the black graph is always going to be infinity, from 1 to infinity. So that means the area under the purple graph, which is a lot bigger, has to be infinity, right? So if in this case, when 1 over x is the smaller guy, and 1 over x, the area under it goes to infinity, the area under 1 over x to the 1/2 has to go to infinity. So let me write down this comparison in our notes here. So an example for this guy is, let's say I have, so in this case, my f of x and g of x look a little bit different. So I have 1 over x is smaller than 1 over x to the 1/2, right? X to the 1/2, the purple graph was always above the black graph, which was 1 over x. And of course, these are both bigger than or equal to 0. So we're only looking at the interval. On the interval, again, from 1 to infinity. So what happens is so in this case, like let's read this statement really clearly. What we're saying is if f of x diverges, now f of x is the smaller guy. If f of x diverges, then g of x must diverge as well. Once again, this makes sense because if the smaller of the two functions diverges, which means that if you take the integral or the area under the smaller function and that goes to infinity, then the area under the bigger function has to go to infinity as well. So this is a really, really important theorem, the comparison theorem, and we're going to use this when we talk about series as well. The really important thing to remember, so one of the most common mistakes that students make for this theorem, so that's the warning over here. Suppose the small guy converges, so suppose f of x converges, we cannot say anything about the convergence of g of x. Now this makes sense. Just because now if the small function, if the area under the small function is finite, you can't really say anything about the area under the big function. And similarly, if the big function is infinity, if the area under the big function diverges, we can't really say anything about the convergence or divergence of the small function. So it's extremely important that we use this theorem in the correct direction. So if you are trying to show that a particular integral converges, try and find something bigger that converges. And if you're trying to find a particular instance where an integral diverges, then try and find something smaller that diverges, which will force the bigger guy to also diverge. So that's essentially the idea here with comparison theorem. You can do this with, all of you can try this on your own with Desmos with different powers of x. So something else that I want to try is, let's look at the graph of 1 over x to the 3 halves. This is really interesting because x to the, well, these are the same color now, which is a little bit weird. Let's take this off. So I have 1 over x. And when I put x to the 3 halves, I actually see x to the 3 halves is a little bit smaller. So this is interesting, right? Because 1 over x, we know diverges. So something smaller than 1 over x, we really don't know. So we're going to have to find something even smaller, maybe, than 1 over x to the 3 halves to really talk about it. So we don't actually know what's going to happen with this particular guy. So we have to be the point I'm trying to make here is that you have to be really, really careful with how you're choosing the function to compare a particular function.